Alright, welcome back now to week 2 of Geology at OTC, and this week we're going to take a look at Plate Tectonics, a scientific revolution unfolds. This is chapter 2. So let's get into this. This is going to be a little bit of a longer video, maybe about 20 minutes. We'll get through all this stuff here pretty quick. So continental drift. This is something that came up before its time that was really ready for it. Kind of a revolutionary thought process about plate tectonics and how they work. The world wasn't really ready for it at the time. And so its proposal was Alfred Wegener, first proposed continental drift hypothesis in 1915, so almost 100 years ago. Published The Origin of Continents and Oceans. And he supposed that there was a megacontinent, supercontinent called Pangaea that began to break apart about 200 million years ago. So here's a picture of Pangaea, and we have Wegener's perspective and a modern reconstruction of it, and you can kind of see how Africa fits in with the east coast of the United States and within South America, and everything kind of fits in there together and started to spread apart 200 million years ago. And so the hypothesis says the continents drifted into present positions. There was evidence for this, the fit of the continents, the fossil evidence. You can see certain fossils that would go in with different shorelines, rock types, and the paleoclimatic evidence that we have at the time of various climates in the rocks and fossils we see. Here we have matching mountain ranges. We see the Caledonian Mountains in Scandinavia matching up with the Appalachian Mountains in North America back 200 million years ago. We have paleoclimatic evidence. We see in the white areas you would see evidence in the fossils and plant life that they had a similar climate 200 million years ago. Now, there were objections to the continental drift hypothesis. It lacked a mechanism for moving the continents. Wegener incorrectly suggested that the continents broke apart through the ocean crust, which was not correct. And there was a strong opposition to the hypothesis from all areas of the scientific community. So really ahead of its time. Now, that hypothesis was correct in principle, but contained incorrect details. And so a few scientists started to look deeper into Wegener's ideas and continue the search for answers. So a renewed interest in this theory came in from rock magnetism. And this says that the rocks have certain minerals in them that become magnetized over time. And this magnetized mechanism is kind of like locking in a secret to the Earth. It shows the direction to the Earth's magnetic poles over time, and provide a means for determining their latitude, position on the Earth of origin. Now we know that the poles wander, the North Pole and the South Pole wander, and so this apparent movement of the magnetic poles indicates that the continents have indeed moved over time. Also indicates that Europe was much closer to the equator when coal-producing swamps existed 200 million years ago. We know that the poles for North America and Europe have similar paths, separated by about 24 degrees of longitude. And this difference can be accounted for if we go backwards 200 million years ago to the time of Pangaea and see the continents put back together. So during the 50s and 60s, a lot of technology came to be that would provide mapping of the ocean floor. And so we came up with an addition to the hypothesis, the seafloor spreading hypothesis, proposed by Harry Hess in the early 1960s. And so we have geomagnetic reversals. The Earth's magnetic fields periodically reverses polarity. We know this. And it takes a long time to actually occur. It doesn't happen overnight. Despite what you might see in some Hollywood movies, the pole reversal doesn't happen in just a day. North Pole becomes the South Pole and vice versa. And we have dates when the polarity of Earth's magnetism changed from different lava flows. That lava really locks in the history of the Earth. And so the geomagnetic reversals are recorded into the Oceanic crust. And in 1963, two scientists came in with the discovery of magnetic strips on the ocean crust near ridges and correlated it with Hess's concept of the seafloor spreading. And so what we see on the ocean floor here is at this boundary, the crust is separating from each other, and we can see this picture's painted this way to show you the differences in polarity of the rocks. It doesn't actually look like this, but when you take a look at the rock samples from cores drilled into the earth, we can see this magnetic reversal. So this is called Paleomagnetism, and it was the most convincing evidence set forth to support the concepts of continental drifts and seafloor spreading. So what are the plates of the Earth? We know that the Earth's major plate systems are associated with Earth's strong, rigid outer layer, known as the lithosphere. It consists of the uppermost mantle and the overlying crust. There are 7 major lithospheric plates. Plates are in motion and are continually changing in shape and size, and the largest plate is the Pacific Plate. Several plates include an entire continent plus a large area of seafloor. So here are the plates. We can see that we live on the North American plate, and in the bottom picture you can see the Pacific Plate being the largest plate of them all. Now, the plates do move relative to each other at a very slow but continuous rate, about 2 inches or 5 centimeters per year. And the cooler, denser slabs of oceanic lithospheric plates descend into the mantle. So we have some plate boundaries we need to talk about, and this is very important here. So be sure to rewind this to the 6-minute 45-second mark if you need to. We know that interactions among individual plates occur at their boundaries. We have divergent plate boundaries, we have convergent plate boundaries, and transform fault boundaries. Each plate is bounded by a combination of the 3 types of boundaries. New plate boundaries can be created in response to changing forces. Now, most of these boundaries are located along the crests of oceanic ridges and the seafloor spreading. Along with well-developed divergent plate boundaries, the seafloor is elevated, forming oceanic ridges. So the seafloor spreading occurs along the oceanic ridge system, and different ridge systems exhibit topographic differences, and these are controlled by the spreading rates of the 2 plates. So here we have an example of what we have in the Atlantic Ocean. You have this magma coming up from the asthenosphere, melting into the rock layers, and forms new rock layers on the crust of the ocean floor. And these 2 plates are moving apart, and they spread apart and lock in the magnetic cycle, and this is called a divergent boundary because they're moving apart from each other. Now we have rifts that occur in these continental margins. The split land masses into 2 or more smaller segments. So here we have continental rifting, where the 2 plates are moving apart from each other and can form a rift valley or a sea. Older portions of oceanic plates are returned to the mantle, and these are circular plate margins. The convergent zone is called an oceanic trench, or a subduction zone. And the average angle of the subduction is 45 degrees, and we'll show you that here in a second. In oceanic and continental convergence, the denser oceanic slab, ocean plates are always denser, sinks into the asthenosphere. Along with the descending plate, partial melting of mantle rock generates magma, and the resulting volcanic mountain chain is called a continental volcanic arc. And we have examples of this in the Andes and the Cascades. So here's the 45-degree angle. The thicker, denser oceanic crust goes into the earth, and melting occurs, and you get these continental volcanic arcs that form. Now, the place where the 2 land masses combine and start to go underneath each other, you get a trench right there in the ocean. Now we can have 2 oceanic plates converge, where 2 oceanic slabs converge, one descends beneath the other, often forms volcanoes on the ocean floor, and if the volcanoes emerge as islands, a volcanic island arc is formed. And Japan and Tonga Islands are examples of this. So here we have 2 oceanic crusts. Again, you have a trench where they meet. Melting occurs and starts to form a island arc, and as the plates move, they create an arc of islands because the plate's moving, but you have the magma in the same place. And this is where Hawaii was formed. You see it's in an arc, and as the plate moves around, the melting continues in the same place, and the plate moves on top of it, forming an arc of islands. Now we can have two continental plates converge. And so they're less dense and buoyant, and so what they do is they actually push each other up. And so the Himalayas, the Alps, and the Appalachians are examples of this. So here's two continental margins coming together, and they form the Himalayas, which has the largest mountain in the world, above the surface, which is Mount Everest. We actually have a mountain in the ocean that's actually much bigger than Mount Everest if it was actually on the surface. Now another type of fault boundary we can have is a transform fault, and this is what we have in Southern California. Plates slide past one another and no new lithospheres created or destroyed. And these make some fracture zones, and so we know the San Andreas Fault and New Zealand faults cut through the continental crust like this. And so here's a transform fault boundary where they're sliding past each other. We know from evidence from ocean drilling that some of the most convincing evidence has been directed from ocean drilling. We can get the age of the deepest sediments and the thickness of the ocean floor sediments, verifying the seafloor spreading and the magnetic reversals in the earth. So we get these core samples from the earth, and we can see the magnetic rifts in the rock cycle. We can test the plate tectonics model by looking at hot spots and mantle plumes, which is what we have in Hawaii, as I said, caused by rising plumes of mantle material. And so these are long-lived structures, and some originate at great depth in the oceans. We can look at the magnetism of the rocks stored on the ocean floor to provide a method for determining plate motions, and both the direction and the rate of spreading can be established with these rock samples. Now in more recent times we have GPS systems, and so we can very accurately measure the drift of the continents with GPS. And GPS has two areas of error. For general commercial use, the error could be as much as 3 to 10 feet. For military and other scientific purposes, they can be as accurate as to within half a centimeter. So here's the motions of the plates. You can see that the North American plate is generally moving towards Hawaii. Hawaii is moving up towards Japan, and the plates all move in different directions. So what exactly drives the plate motions? The researchers agree that convective flow in the mantle is the basic driving force of plate tectonics, and convective flow is kind of like boiling a pan of soup or rice on the stove, and you see that boiling action from below come up to the surface and then go back down. So forces that drive the plate motion includes a slab pull and a ridge push. So here we can see a slab pull where they're pulling each other down. We also see a ridge push where the plates are being pushed away from each other. We know that we have models of plate mantle convection. The theory of plate tectonics provides examples for Earth's major surface processes and the distribution of earthquakes, volcanoes, and mountains, and the distribution of ancient organisms and mineral deposits that we see on the Earth. Well, that's it for Chapter 2. We came up to under 15 minutes, so be sure to rewind to the certain sections you need to review, and we'll see you next time.